All right. In this example, we have a color P, slides. Let me do this. So we have a color P. It slides along the semicircular rod. Rod is shown with AB, and it has a radius of 200 millimeters. Now we are told that the rod rotates about the pin A here, and we know the angular velocity and angular acceleration of this semicircular rod. Right? Angular velocity is 0.8 radian per second in counterclockwise, and alpha or angular acceleration is 0.5 radian per second in clockwise direction. Now, at the position that we see right now, right here, at this specific position, all we know these values, and we're asked to find the velocity and acceleration vectors for this point, for a color P. Right? You want to know what is VP and AP, those vectors. You want to find those vectors. We're also told that the velocity of P relative to the rod is constant, and it's 120 millimeters per second. Now, again, I start with where do I want to put my frame and which part I want to attach it to. Well, in this case, I'm given the velocity, the relative velocity of this color to this curved semicircular rod. So I'm gonna I have to put the frame somewhere on the rod, so I can use this relative velocity, velocity of P with respect to the rod. So I'll put it on the rod, and I'll put it at point A. I'll just put it here. So that will be my local frame. This would be X and Y. Now, to make sure that nothing is confusing, I'll just change these two to X and Y. So these are going to be our local coordinate frame. These are going to be axes of our local coordinate frame. Okay, so we are asked to find the velocity first. So I'm going to write the equations for velocity. VP, well, this is my local frame. I'm going to study the color P that's moving along this curved rod. So VB is equal to VA plus V relative plus omega cross R. These are axes. These are all vectors. Now, VB, I'm studying point P, so this should be VP. And also should be in blue. VP. So V relative I'm given at this specific moment. VP, I know nothing about it. Let's start from the beginning. I don't know its direction. I don't know its magnitude. Pretty much nothing. VA, well, it is 0. Point A is not moving, so this is 0. V relative, well, I know its magnitude is 120 millimeters. And think about it this way. Think about this, that we are studying this point P at this moment, and this is the local coordinate frame. This velocity is just towards right. So it's in I direction at this moment, right? That if it slides up or slides, if it slides towards B or it slides towards A, we're going to have a different story. But at that specific moment, it's along I. So I know its magnitude and I know its direction. So I can just write it here. V relative as a vector it would be 120. I'm given the magnitude in I direction. And this is the vector. The next one would be omega cross R. Well, let me write it first. Omega cross R. Now, omega cross R, well, this case, the axis, the local coordinate frame, is rotating around its origin. The origin is point O, and the whole axis, the whole frame is rotating around the axis at point A, and the whole frame is rotating around point A with omega, which is equal to 0.8 radian per second. So it is rotating, omega cross R exists, and I'm studying point P, which is not exactly on the origin, and there is an R. There's a distance from that point and the local coordinate frame. We said R is the distance of the point we're studying from the local coordinate frame. So that R exists, which means omega cross R exists. Now, what is the magnitude of that and what is the direction? Well, the magnitude, well, let me just put it first here. This is R. Right, this is R. Omega is counterclockwise, which means omega cross R would be in this direction. Well, let me draw it here. If it is the imaginary line between point A and point P, right, this would be omega cross R, assuming that omega is in this direction, omega A, B. Well, I'm just going to write omega since we are just showing it with omega here. Omega is the rotation of the frame, angular velocity of the frame. Now, omega cross R, well, to do that, I need to find R first, right, the distance. So R is the square root of 200 squared plus 200 squared. And I'll get R as, I have the value, 282.84 millimeters. Now the direction, well, here's the direction. If this is the horizontal line and this is the vertical line, we have a rectangle, a triangle that these two sides have the same length, like the radius, which means this is 45 degrees. This is 45 degrees. And this is 45 degrees. So let's plug in the numbers. I'll get, well, omega cross R would be R, which is 282.84 times omega, which is 0.8, times, I'm going to write the rest here, times cosine 45i plus sine 45j. Do that, you'll get 160i plus 160j. So put things together, we can find VP. Right? We know everything. We know both magnitude and direction of omega cross R. So from there, all of this, you can actually find VP as a vector. Would be 120i plus 160i plus 160j. Just I'm summing up the components, right? So we get 280i plus 160j millimeter per second. That would be the velocity of point P in terms of a vector, or represented in a vector term. Now, looking at the acceleration, we're asked also to find the acceleration. I'll go to the next page. The acceleration, well, same story. I'll write AP is equal to AA plus A relative plus alpha cross R plus 2 omega cross V relative plus omega cross, missed the cross there, omega cross R. These are all vectors. Now, looking at this one, well, A is not moving, right? Point A is fixed, so there is no acceleration there. AP, I know nothing about it. That's what I'm trying to find. A relative, let's see, A relative is a vector. And then it is, well, this is point P. If I draw this, the only component I have is a normal direction. Right? This is going at this specific point, is rotating around this point. So that would be, let me do it here, that would be point O. It's just rotating around that point at a specific point, relative. When we talk about relative, it means our frame was here, right? It means just fix the frame. This semicircular rod is not rotating anymore. How does this move? At this specific moment, it's going this way. So the only component it has, well, there is no tangential component because the motion is horizontal. The only component is in normal direction. That would be your component. Right? So it's a relative normal. And we can find it with, well, we know V relative, so it's pretty good. So we can use V squared over R. V relative was 120. We were given squared over R is the radius 200. That will give you 72 J millimeter per second. Now, the second component, so for this, a relative, we could find both magnitude and direction. Alpha cross R. Alpha cross R is, let's go there. Well, let's see what we know about this. This is the point. This is R, the distance. Point P from the origin. And alpha is clockwise. So alpha cross R would be in this direction. We're going to get the vector. Let me assume that this is the imaginary line from A to P. So alpha cross R would be perpendicular to R in this direction. And we need to know this angle, and this angle is 45 degrees. This angle right there. This angle. Since this angle is 45, these are perpendicular, the other angle is 45. So we plug in. We know R, we know alpha. Alpha is 0.5 times R, which I calculate that, 282.84. And I decompose the vector in X and Y. So the minus cosine 45I minus sine 45J. Do that, you'll get minus 100. Oops. You'll get minus 100I minus 100J. Then next component, well, for this one we know the magnitude and the direction. Next component would be 2 omega cross V relative. Keep in mind that in this case we have both alpha and omega because local frame is rotating around its origin. It's different a little bit from previous examples. Well, the magnitude we know, 2 times omega, we're given 0.8 times V relative. Well, V relative also we're given 120, the velocity of color P with respect to point A. And let's see what is the direction. Well, 2 omega V relative is always perpendicular to V relative. If you remember, we were talking about this, introducing the terms. This would be, or V relative, we know that. Right, so let me write it this way. So this is V relative, which means that we'll get 2 omega cross V relative perpendicular to V relative. Let me just write it. So that would be your vector, perpendicular to V relative, which means it's in J direction. This gives you 192 in J direction. And the final term, so in this case also we know the magnitude and direction. The final term is omega cross R. And about this one, when we talked about the direction, we said the direction of this is always from the point we're studying toward the origin of the local coordinate frame. It doesn't matter what is the direction of omega, as long as this term exists, it's always from the point we're studying toward the origin of the local coordinate frame. So the values, let me just plug in omega squared times R. This is the magnitude. And to find the components, well, pointing from the point we're studying towards the origin of the local frame, this way. That would be the direction. And this angle here, this angle here is 45 degrees. Which means if we decompose that, I'm going to write the rest here, would be minus cosine 45I plus sine 45J. Once you do that, you'll get minus 128I plus 128J. So, knowing all these, we can just put them together and find AP, because for omega cross omega r, also omega cross r, we also know the magnitude and direction. So AP would be the summation of these terms. If we sum them up, you get minus 228 in I direction and plus 292 in J direction, would be millimeter per second squared, and that's the acceleration of point P. So we got the acceleration of point P and the velocity of point P, and that's what we were asked to find for this problem.